Is that,
Yes,
can you
we
see
can
that?
see.
Yes,
Yes,
okay.
we
Yes,
So
that's
here we go,
clear.
everybody. Thank you very much.
Good afternoon, everyone. My name's Chris Eden. I'm a director of the Organics Group of Companies based in Spain. I'll be making a presentation together with my colleague in New Zealand, Jurgen Thiel. And today we'll provide some insights about the anaerobic digestion of organic waste. We'll look at the technology used in the industry, this with particular regard to its value in producing biogas as a commercially viable source of renewable energy. The purpose of this presentation is to raise awareness about the challenges faced by the waste management industry and to look at anaerobic digestion as a potential solution for the treatment of organic waste and wastewater. We'll start by touching on the growing problem of waste generation worldwide and its environmental, social, and economic impacts. We'll have a brief look at how AD works and then discuss the various techniques used in anaerobic digestion, including the different reactor types, operating conditions, and feedstock options. Throughout the presentation, we'll provide you with several examples of the technology. Before I start, though, a word about our company, Organics. We've been involved in environmental engineering since 1985, a trajectory that's touched on most aspects of landfill engineering, with particular emphasis on the control and use of biogas. This includes not only anaerobic digestion of organic material, but also in using landfill sites as the principal anaerobic digester for the generation and storage of biogas, as well as the production of renewable energy. Latterly, we've been involved in the installation of equipment for anaerobic digestion and the fabrication of equipment for the production of biochar, especially from organic materials, including digestate from the anaerobic digestion process. The world is facing a growing waste management crisis that affects every country and everybody. The situation is well presented in this brochure prepared by the World Bank. As urbanization, economic development, and population growth continue, the World Bank projects a staggering 70% increase in global waste generation, from 2.01 billion tons in 2016 to 3.4 billion tons by 2050. Food and green waste make up a significant proportion of the total waste generated globally, accounting for up to 40%. While Africa currently generates the least amount of waste compared to other regions, it still faces unique challenges in terms of modernizing and improving its waste management practices. Shockingly, at least 1/3 of this waste is currently mismanaged through unsustainable practices like open dumping or burning, leading to environmental, health, and economic consequences. This alarming situation underscores the urgent need for effective and sustainable waste management solutions to protect our planet and its inhabitants for generations to come. Moreover, the inefficient use of resources and the failure to recover valuable materials from waste streams leads to significant economic loss, not to mention the missed opportunities for job creation. So something needs to be done. Recently, anaerobic digestion has become de rigueur for the treatment of organic waste. Anaerobic digestion is a sustainable waste and wastewater treatment solution that breaks down organic matter in the absence of oxygen, reducing pollutants and pathogens. This process yields biogas, a renewable energy source, and provides multiple benefits such as nutrient recycling and economic advantages. As shown in this diagram, anaerobic digestion is a biological process that occurs in the absence of oxygen, where microorganisms break down the organic matter into biogas and digestate. The feedstocks from AD can come from a variety of sources, including manure from livestock, wastewater with biosolids from municipal sewage sludge, as well as other organic waste such as fats, oils, grease, and crop residues. These feedstocks can be digested in isolation or co-digested to optimize the AD process. During the process, the feedstocks are broken down by the microorganisms in an anaerobic environment, typically within a sealed reactor or digester. And the end products of this process are biogas and digestate. Biogas is a renewable energy source composed primarily of methane and carbon dioxide, which can be used as a renewable fuel, while digestate is a nutrient-rich source that can be used as an organic fertilizer or soil amendment. The diagram also highlights the potential of using biogas to power the AD process itself. In this next diagram, we show the different types of technologies that are used in anaerobic digestion. Each of these processes has its pros and cons, and each can be suitable for any given situation with regards to how the feedstock material is collected and fed into the system. We'll look at the following techniques. Firstly, the covered lagoon anaerobic reactor. Secondly, the continuously stirred tank reactor, the most commonly used technology for AD projects. Thirdly, the temperature-phased anaerobic digester, which is a variation on the last technology. And finally, the dry cell anaerobic digester. We won't be dealing with the other items listed on the diagram, other than to mention that these are techniques for conditioning biogas before it can be used. Once it's been cleaned and prepared, biogas can be used to generate electricity or heat, and used as a vehicle fuel in the form of compressed biomethane. So the first technique we're going to be looking at is the covered lagoon anaerobic reactor. It's a process that treats liquid waste with low solid content in large, shallow earthen basins covered with a gas-tight membrane. The anaerobic microorganisms break down the organic matter, producing biogas and treated effluent. The process is suitable for waste such as animal manure, industrial wastewater, and diluted food processing waste with a solid content of less than 3%. Lagoons are designed to have a depth of between 4 to 6 meters and a large surface area with a retention time of around 30 to 60 days. Biogas yield depends on the feedstock type, the organic loading rate, and the operating conditions, while the treated effluent can be used as a fertilizer. This photograph shows a covered lagoon installed on a palm oil wastewater treatment plant in Indonesia. The lagoon is purpose-built with a series of internal injectors that encourage methane production. The biogas generated must be cleaned of impurities before it can be used. Operating parameters include that it can operate between 10 to 40 degrees centigrade, depending on the climate and the availability of heat. But of course, this has a direct effect on the retention time, which can be between 30 and 60 days, depending on the feedstock and the temperature. The pH is maintained between 6.5 and 7.5 for optimal microbial activity. After the biogas has been generated, it must be prepared for use. And this includes stripping the biogas of impurities, one of which is hydrogen sulfide, which can be particularly corrosive to mechanical equipment. This photograph shows the biological hydrogen sulfide stripping system used on a palm oil mill effluent lagoon. In the next photo, this illustrates the use of biogas from the digestion of palm oil mill effluent. In this case, the methane is being used for the generation of power to provide electricity to the palm oil mill itself. I'm now going to hand you over to Jurgen Thiel to discuss the thermally phased anaerobic digestion technique.
The continuously stirred tank reactor digester, or CSTR digester, is a workhorse of the global anaerobic digestion industry since decades. Modern versions have cylindrical or egg-shaped tanks with a synthetic double membrane roof for biogas storage. CSTR is a type of anaerobic digestion where the feedstock is continuously mixed in a cylindrical egg-shaped reactor tank. bacteria break down organic matter in the absence of oxygen, suitable for liquid feedstock with a solid content of up to 12%, for example, wastewater treatment plant biosolids or industrial wastewater. As minimum solids content, we recommend 0.2 to 0.5% solids content and a minimum COD of about 3,000 milligram per liter. Feedstock should be free of large particles and grit to prevent sedimentation. Myself, as an anaerobic digestion advisor for over 40 years, I have basically extensive experience with many different designs of CSTR digesters, many different mixing systems, and we will discuss some of that here in this presentation. Here is a schematic basically showing that for manure application, the feedstock will be pumped into the digester either at the bottom or the top as shown here, and the mixing system that can be mechanical or hydraulic with jet mixing or biogas recirculation through the tank with the aid of eductor tubes brings the feedstock in contact with the resident sludge of the anaerobic bacteria. Feedstock should be free of large particles. This is a design from 1990, one of the first agricultural digesters in New Zealand, working on the sheep yard droppings as well as high fat waste from the rendering operation at a large slaughter facility. In the old days, the biogas was stored in an external pillow tank. Normally, these days, we have it all under the roof in the double membrane roof. Here, a more modern application with a fixed roof CSTR digester from the largest food waste digester in the Southern Hemisphere that was designed and constructed in 2000 in Sydney. And the biogas was basically used as it was generated for power production and for drying the digested residue. At Organics, we offer, in addition to traditional CSTR design, CSTR Plus, where we add features to increase the digestion efficiency and the organic loading rate. Mixing systems like mechanical, gas injection, or pump recirculation are available for all those applications. Temperatures could be mesophilic or thermophilic, maintained by external heat exchangers or internal heating coils. Solids residence times, depending on the concentration of the feedstock, between 10 to 40 days. And of course, temperature plays an important role. And a standard CSTR without the plus feature may be 2 to 5 kilograms COD per cubic meter digester per day, a suitable organic loading rate. With the plus feature implemented, it is typically double that amount. It could be triple depending on the nature of the waste. Critical is, as always, balancing the biogas production and process stability. Here, an example from New Zealand where the plus feature, a recuperative thickener, is basically housed in a container that is connected up to an existing 50-year-old digester tank, which allowed to double the throughput and the COD loading rate, the permissible COD loading rate, to this already existing digester tank. So it can be retrofitted. The feature is basically shown with this process flow scheme in the red arrows, that digester contents are continuously pumped through the thickener. The thickened sludge is returned into the digester, and the excess filtrate that has been removed can be disposed to further treatment or other applications. And the thickened sludge, part of it can be also forwarded to sludge dewatering to make sludge cake for export from the plant. Typical thickeners can be drum thickeners, but there are many other options that we can choose from. All have in common low power consumption, fully automated, low maintenance. A weekly clean is normally sufficient, and low polymer consumptions, 4 to 5 kg polymer per ton dry solids. For example, in dewatering, the polymer dose will be 2 to 3 times that amount. Here, an example of the filtrate removed from a municipal wastewater treatment digester. And in this application, the recuperative thickener was here in a separate building and allowed basically to run the whole sludge load in a single tank permitting the clean out and rebuilding and optimization of digestion in the other tank. And then one could basically swap over the thickener to the reconfigured tank and also upgrade the tank that was before running at double the load due to the recuperative thickening or the plus configuration. In high fat content waste applications, the plus feature is possible, but typically would not be as advantageous as in standard CSTR applications. Continuous mixing prevents formation of dead zones. The biogas yield depends on feedstock type, organic loading rate, and operating conditions. Typical biogas composition could be 55 to 75% methane. High fat content gives high methane content in the biogas. And we use a bioengineering approach to optimize the digester bacteria culture for fat digestion. This is an application of a CSTR plus feature in a recent dairy factory commissioned by us 5 years ago for the removal of DAF sludge and other high fat wastes from the dairy factory. Now, the big picture that this is based on is the standard known flow diagram of carbon and electrons in anaerobic digestion. Complex organic polymers are converted to volatile fatty acids, long-chain fatty acids. They are broken down by symbiotic bacteria into acetic acid, hydrogen, and formic acid. And then hydrogen and formic acid and acetic acid are removed from the digestion broth by methane bacteria to produce CH4 and CO2. So methane bacteria remove acid in essence and produce gas, therefore leading to acid removal and neutralization of the pH in the digester. If the flow from the top into the digester is higher, then the removal activity the methane bacteria can catalyze, the digestion process is likely to acidify and basically self-inhibited. Other inhibitions are ammonia. Ammonia is produced from the protein degradation, and ammonia nitrogen is also gradually inhibiting methanogenesis. And long-chain fatty acids from fat degradation are very potent inhibitors of methane bacteria. So the system has to be well balanced to have a stable COD flow from the top to methane and CO2. So if we look at the big picture, then we see that mesophilic ranges have typically half the capacity for COD loading at the top, at the complex hydrolyzing bacteria level, and also half the capacity of the thermophilic bacteria. So mesophilic bacteria, usually half of the capacity of the thermophilic bacteria for methane production and COD removal. In order, therefore, to adjust a digestion process, one can couple two CSTRs in series, have a digestion stage separation, and we'll show an example later on in this presentation. And this digestion stage separation adds robustness and resilience to the digestion process. The initial hydrolysis stage produces acids, and the final methanogenic stage removes the acids in a separate tank. Suitable conditions, I will not discuss this here in detail because we're running out of time. Happy to do it in questioning. I'll document it here in this table, as well as the inhibition thresholds for various process parameters like temperature, pH, sodium, potassium, volatile fatty acids, and COD level in the digester. Again, I would prefer to do that in the questioning rather than in this presentation here now. One application of separating the phases of anaerobic digestion into two sequential CSTR digesters is temperature-phased anaerobic digestion, or TPAD. TPAD, basically dewatered sludge or anything else like municipal solid waste, can be macerated and then pumped into a thermophilic reactor where the hydrolysis happens twice as fast as under mesophilic conditions at 55 to 65 degrees with a solids residence time of 1 to 2 days, turning a proportion of the loaded material into acid. And the acid is then pumped into a methane reactor, and we change this, that the hydraulic residence time is preferably 8 to 10 days, not 5 days as it was before shown in the diagram. The solids residence time, typically 10 to 15 days in the mesophilic reactor to degrade the products of thermophilic metabolism. The hydrogenized solids of this type 1 temperature-phased anaerobic digestion, temperature-phased because a thermophilic phase is followed by a mesophilic phase. The solids can be removed for dewatering and then composting, and the centrate can be used as feedstock to recover the ammonia in ammonia recovery facilities. This is a typical type 1 TPAD. Type 2 TPADs are slightly different, where we make the first digester much bigger than in the type 1 TPADs, getting a long solids residence time in excess of 15 days, and therefore quantitative breakdown of the organic matter under the preferable thermophilic temperature at higher rates, and then pumping that from a type 2 system through the mesophilic reactor, very similar to the mesophilic reactor in a type 1 TPAD system. Here an example of a type 2 TPAD from the wastewater treatment plant in Christchurch, suitable for a wide range of feedstocks. It gives us higher biogas yields because at the high temperature and long residence time in the first thermophilic stage, we're breaking down complex polymers much more extensively than we would do that in a type 1 TPAD. Typical biogas composition, 60 to 70% methane, and ammonia could be recovered, is not recovered in this case, but could be recovered after the first stage because the breakdown of the carbon has been nearly quantitative, and so the protein hydrolysis and breakdown as well. A case study now for this startup of the type 2 TPAD in Christchurch. The first stage, acetogenic thermophilic phase at 50 to 60 degrees. The second stage, methanogenic reactor at 30 to 40 degrees. The first stage had a volume of about 15,000 cubic meters in 2 tanks. The second stage, a volume of about 18,000 cubic meters in 4 tanks. Because of the configuration, we've heard the first stage 15 to 25 days SRT, and therefore a neutral pH. The acid production was handled by thermophilic methane bacteria, and it gave us a much better yield of biogas. And the second stage was basically used to remove any residuals of degradable COD from the effluent from the first stage. So the original digester plant, commissioned in 1961, had 4 times mesophilic reactor tanks, and my team was then appointed in 2010 to design the commissioning and startup of the thermophilic stage using mesophilic bacteria as seed sludge. And I'll bring you an example in this case study how that can be done. With the startup regime we designed and implemented, we increased the biogas production by 67%, estimated 70% from the increased solids residence time, and the rest came 30% from an increase of the activity in the thermophilic digester. So it's a combination of beneficial events that gave us the significant increase of biogas production. The volatile solids destruction efficiency increased by 19% to a total efficiency of 77%. And the solids content in the digested solids basically was at slightly less, but at the same time, the volatile solids content of digested solids increased. So decreased, sorry, from 69% to 62%. Evidence that the organic matter has been degraded more quantitatively. Here is the actual profile. The blue bars give us the activity of gas production measured as methane in the mesophilic stage, and the red what was produced in the thermophilic stage. And as you see, this is in 2010, so reported in 2011. once the thermophilic tanks were operated in mesophilic conditions, the extra working volume they provided allowed a gas production increase from about 450 normal cubic meters per hour to about 650. So simply because of the added working volume. But then once we did changed the operating temperatures and turned the mesophilic sludge through thermophilic acclimatization into thermophilic bacteria, radically the thermophilic bacteria took over the COD flow and turned the total load in about 750 normal cubic meters per hour of methane, of which about 20% came from the mesophilic activity in the second stage, and 80% of that increased gas production came purely by the type 2 cultures that was established in the thermophilic stage. So what it tells us is there are different ways you can do temperature-phase digestion. And the way we designed and implemented in Christchurch, we also have implemented at other facilities, gives that at the end of the day better results than the traditional type 1 TPAD design. This type 2 TPAD can also be applied to non-municipal waste. Here, this is a design that Organics is offering for fruit and vegetable waste in various places. This would probably even end up in South Africa if the project is accepted for implementation. We would have a mixed waste with a very low contaminant level that is further decontaminated from plastic and paper and timber residues. Glass and metal would be absent from the waste by default. Those rejects will be removed from the facility after handpicking a trommel screen that removes other materials that would not be picked up by the handpicking. Then a macerator turns it into a small slurry of small particles, and in a deep day tank pH dosing to add alkalinity, we would produce the feedstock for a type 2 thermophilic design. The reactors would be operated under the conditions we discussed before for type 2 applications. Sand and silt would be removed from the bottom and scum from the top, and what's left over after thermophilic treatment then polished in a mesophilic reactor, again with recuperative thickening to increase in a CSTR plus configuration to increase the reaction rate and the efficiency of the mesophilic bacteria. And biogas can then be put to various applications, as a vehicle fuel, etc., etc.
So the final technique we're going to be looking at is the dry cell anaerobic digestion. This is a technique in which organic material is stored in a chamber for enough time to ensure complete digestion of the organic content. The solid content of the feedstock is much higher, generally between 20 to 50%, and the only water that's added is generated by the process itself. Digestion takes place in a sealed, oxygen-free reactor where microorganisms break down the organic matter, producing biogas and digestate. Dry cell requires less water and smaller reactor volumes, reducing the overall footprint of the digestion plant, and it can handle a wider range of solid feedstocks, including those not suitable for wet digestion. There are two types of dry cell anaerobic digestion. The diagram shows a garage-type reactor in which the feedstock is loaded and unloaded using front-end loaders. The biogas yield is typically between 50 and 60% methane, with up to 40% carbon dioxide, and the feedstock is left in place for around about 30 days. The second type is a plug-flow cell reactor. These are used primarily at dairy operations where manure is collected by scraping and then moves through the reactor as a plug. Using this technique, there is usually minimal mixing. Biogas yields are similar to the garage-type reactor, and in both cases, digestate from the processes can be used as a fertilizer or soil conditioner. But generally, this requires further processing, such as composting or drying, depending on how it's going to be used. The images are from a project that we installed in Bali, Indonesia. The plant was a dry cell plant treating municipal solid waste. As a first step, the feedstock had to be separated using a series of trommels. The organic fraction was then fed into a series of dry cell digesters, and in this case, garage type digesters, and it was left there for around about 30 days. The produced biogas was cleaned of impurities and then used in the generation of power. In this case, the energy was used on site as well as being injected into the national power grid. So in conclusion, we can say that anaerobic digestion is a versatile, proven and sustainable technology for biogas production and is an appropriate technology for dealing with vast amounts of organic matter that are being generated and are projected to be generated in the future. We've covered several techniques, including the ones listed here, and in particular, we can say that its value lies in, firstly, the production of biogas, which is a versatile renewable energy, and in reducing the dependence on fossil fuels, as well as mitigating the greenhouse effect. It reduces the volume of waste that goes to landfill and the problems associated with odor. It produces a nutrient-rich digestate and supports local economies through job creation.